My last video got cut off unexpectedly there, but that's okay. I'm just going to pick up where I left off. So I think what we were doing is we were talking about this little equation right here. I had mentioned that this dot product is equal to this dot product from a result that we have way back in chapter 3. And then we use the assumption of symmetry to say that A transpose is equal to A. Okay, so this dot product being equal to this one. Now the AV1 and the AV2, I'm going to use these with the assumption that V1 and V2 are eigenvectors corresponding to different eigenspaces of A. That means that, well, let's say that V1 corresponds to the, let's just say eigenvalues right here. Let me change that. Eigenvalues, lambda 1 and lambda 2 respectively. Then that means AV1 is equal to lambda 1 V1. So I can make that change here. And then AV2 is equal to lambda 2 V2. Okay. Now this equation right here, if I were to subtract this right-hand side over to the left-hand side, then I would have a difference of two scalars times a dot product, v1 dot v2, v1 dot v2. I could factor the dot product out, and I'd be left with this equation here. Lambda 1 minus lambda 2 times the dot product of v1 with v2 is equal to 0. Both of these are scalars. Remember, the dot product gives us a scalar. So I have a scalar times a scalar equals 0, and from your zero product property, one of them has to equal 0. But we know that this one is not equal to 0. If they were, then lambda 1 would equal lambda 2. But we're assuming that lambda 1 and lambda 2 are the eigenvalues corresponding to different eigenspaces. That only happens if they're different numbers. So this is not equal to 0, which implies that v1 dot v2 is equal to 0. And remember, that's what we wanted to show in the first place, because this is what establishes that those two eigenvectors are orthogonal to each other. Okay, so here's where we sort of wrap that proof up at the top. Okay, so this is the last thing we have to do in this section, again, because we only cover half of 7.2. It's a relatively short section for us. But what we want to do now is, after laying some groundwork with theorems, we want to talk about the process of orthogonally diagonalizing an n by n symmetric matrix. Remember, you can only do this if the matrix is symmetric. But anytime you have a symmetric matrix, you can always do this. Remember, there's that equivalence. So assuming we have a matrix A that is symmetric, we proceed in a way that's essentially the same as diagonalizing the matrix with an extra added twist of sorts. We start by finding all of the eigenvalues for A, and then using those we find a basis for each eigenspace of A. This is the same thing that we do in chapter 5 for diagonalizing a matrix. Now here's, in step 2 is where we go one step further. Normally, the bases for the eigenspace of A would be loaded as columns into the matrix P, and then that would be the matrix that diagonalizes A. However, depending on how you find this basis, putting all of those vectors into P may not give you an orthonormal set. Remember, if matrix P is orthogonal, then its columns need to form an orthonormal set. So what we do is we still take all of the basis vectors that we found in step 1, toss them into a set, and then, back that up. We don't put them into a set right away. What we do is we perform the Gram-Schmidt process to each of those bases so that each basis becomes an orthonormal basis, okay? So let's suppose you have like 3 eigenspaces for this matrix A. I have 3 orthonormal bases that I've obtained after getting to step 2. 1, 2, and 3. By themselves, they're all orthonormal sets. If I put them all together, will the set that represents the union of those 3, will that still be an orthonormal set? Well, because of the theorems that we just proved, the answer is yes. Because they're orthonormal, all of those vectors are unit vectors. So that means if you throw them all into the same set, you still have a set full of unit vectors. But the next question is, are all of the vectors orthogonal to each other? Well, that answer is yes as well, because of the theorem that we just proved, which says that vectors from different eigenspaces are orthogonal to each other. So that's automatically going to work out just fine. We just apply Gram-Schmidt to each individual basis and then throw everything into one big set it's automatically going to be orthonormal at that point. We can use those as columns in the matrix P, and then that's going to be the matrix that orthogonally diagonalizes our matrix A. So I'm going to walk you through one example here. What we want to do is orthogonally diagonalize this matrix A. And you can see by inspection this is a symmetric matrix. Remember, this would not work. We couldn't do this if this matrix was not symmetric. So first things first, we need to find the characteristic equation or characteristic polynomial for A. That's the determinant of lambda I minus A, which would be this determinant, lambda minus 1, 1, 4, positive 1, lambda minus 4, negative 1, 4, negative 1, lambda minus 1. Okay, and for the sake of time, we're not going to walk through the evaluation of this determinant. We know how to do these. It just takes a little bit of work, but if you evaluate the determinant and then factor the cubic polynomial that you end up with as a result, you get this, lambda plus 3, lambda minus 3, lambda minus 6. That means we have 3 eigenvalues. If I set that equal to 0, then my eigenvalues are plus or minus 3 and then 6. That gives us 3 eigenspaces. So the first one, lambda 1, let's let that be negative 3. And then remember, the way that we find a basis for this is we substitute this into our into our matrix, and then we look for the null space, a basis for the null space of that eigenspace. Okay, that process can sometimes be a little bit lengthy. I'm gonna, again, just for the sake of time, go kind of get us to the new stuff quickly. So in this case, we end up with the following basis for that null space: 1, 0, 1. Lambda 2 is going to be the eigenvalue 3. And remember, there's stuff that happens in here, right? There's more work than what I'm showing, but it's all work you've done before. A basis that we would naturally get by looking for the null space, which is the eigenspace, or a basis for the eigenspace corresponding to the eigenvalue 3. You would end up with this basis. It's negative 1, negative 2, 1. Lambda 3 is going to be 6, and the basis that we would get for this eigenspace is going to look like negative 1, 1, 1. Okay, now notice in this particular case, and this is the nicest case, we call these simple eigenvalues, which means that their algebraic multiplicity is 1. And remember, algebraic multiplicity it tells us how many times a eigenvalue shows up or as a 0 in this characteristic polynomial. In other words, there's no exponents on any of these factors. Each one only appears once in this factorization. This is the nicest case when you're doing this by hand, because Gram-Schmidt is almost not even Gram-Schmidt at this point. We have to convert these bases, each of these bases individually, into orthonormal bases. But the Gram-Schmidt process is a lengthy process when you have multiple vectors in a basis, when you're dealing with a higher dimensional eigenspace, because those formulas get messier and messier. You know, the more the work becomes longer the more you have in here. If all you have is one vector and we're just looking for an orthonormal basis, Gram-Schmidt is really just normalizing whatever vector is in there. So I'm going to say GS for Gram-Schmidt. All I need to do is normalize this vector. This would be the vector 1 over root 2, 0, 1 over root 2. If I use Gram-Schmidt on this one, which in this case just looks like normalizing the vector, I'm going to get the vector, let's see, this would be negative 1 over root 6, negative 2 over root 6, and positive 1 over root 6. If I use Gram-Schmidt on this one, I'm going to get negative 1 over root 3, 1 over root 3, 1 over root 3. Okay? So, based on the work that we've done already, each of these sets is now orthonormal, and if I put them all into one big set, we know for sure it's going to be orthonormal as well, so that I can use these as the columns of P, and that's going to orthogonally diagonalize my matrix A. So P would equal the following matrix: 1 over root 2, 0, 1 over root 2. Negative 1 over root 6, negative 2 over root 6, 1 over root 6. Negative 1 over root 3, 1 over root 3, 1 over root 3. And that's it. And this is a question that I answered back in chapter 5, but it holds here as well. What happens if you computed these eigenspaces but in a different order? What if you found, what if you were calling lambda 1 6, and lambda 2 negative 3, and lambda 3, the other positive 3? Then that's fine. These columns would appear in a different order, and all that really does is when you represent your diagonal matrix in the form PTAP, it's just going to switch around where those diagonal entries show up. Remember, if these are the columns that I use and they correspond to the eigenvalues negative 3, 3, and 6, then in my diagonal matrix, going from the top left to the bottom right, my diagonal entries would be negative 3, 3, and 6. But if I swapped maybe these two columns, all that's going to do to my diagonal matrix is swap the positions of these two diagonal entries. So it's basically, that's just to say that you don't need to worry about putting these columns in the correct order, because there's not a correct order, as long as you know that changing the order just changes the entries on the diagonal on the main diagonal of the diagonal matrix that A is similar to, orthogonally similar to. Okay, so that's going to be it for section 7.2.